I want to continue on with our Newton-Raphson discussion, but I want to go for the multi-dimensional Newton-Raphson. So here is the basic idea that we had just covered in Newton-Raphson, is that we take, when we want to find a new guess, we take the old guess and we subtract, and we're really using the slope, right? So we're taking the what that guess generated, the y value, if you will, and the slope at that spot, and finding an intersection where it intersects the x-axis, and that becomes its new guess, right? That's what essentially what we've done here. It's really y equals mx plus b, but we've just flipped the thing around to be able to find where we ended up intersecting right here. So we rewrote that thing out so that we have the slope times the difference between the guesses is equal to the original function, and we can shorten that down into a matrix, or symbols that will represent a matrix. So this guy for this A right here is going to be a multi-dimensional thing, right? And that slope. And if you have a multi-dimensional slope, there's a name for that. And that is, okay, so here is the basic equation is symbolically. And that slope is instead a Jacobian. And if you recall, the Jacobian is the partial differential of each of that function, or each function along there with respect to each of the variables that's in this function, right? So this is going to be a square matrix, and then that's going to be, the x is going to be a delta, and that's going to be a column, a column array, and then it's going to be equal to b, which is going to be a column array, but that's just those are just going to be the functions for all of them right here. So what we're going to do, so the easiest way to understand how this gets implemented is to see it in a 4-bar mechanism. So that's only 2 dimensions, right? So we said a single dimension, so let's look at a 2-dimensional one. So in this 2-dimensional one, we have 2 functions. One of them is the x position, and one's going to be the y position, right there. And you'll notice we have 2 variables that we don't know, right? So that's going to be 2 equations and 2 unknowns. So the function 1 is in the x direction, and where it's a function of theta 3 and theta 4. And in the y direction, it's a function of theta 3 and theta 4. So what we can do is we will represent our Jacobian right there. You can see that's the partial differential of this equation with respect to theta 3. Right there, you can see that the only one of these is a function of theta 3, so the partial derivative of this is going to be a negative sine, right? It's a b times cosine right there, so that's a negative b. And then you see the same thing, the partial derivative of this function with respect to theta 4 is going to be, the only one they have is a negative c times cosine of theta 4. So that becomes the c times the sine of theta 4. And the same thing here. So here's the second function, partial derivative with respect to theta 3. That ends up being this guy right here. So that's just the derivative of sine. So that's the cosine, positive sine. And then a last one with respect to theta 4. So that's again negative c sine of theta 4. That becomes the negative c cosine theta 4. So that right there, those are the Jacobian slopes of the thing. Our x, that right here, that's just going to be the delta of the theta 3 guesses and the theta 4 guesses. And then lastly, we have the original function itself over here is b. So when we're putting together these matrices, we look like that right there. And what we want to try to do is minimize these 2 variables right here. So those are going to consider the norm, which is the square root of the sum of the squares of these, and we want to make that very small, right? So we want below a tolerance. So it's very similar to that Excel thing, that solver, where we took that the difference between the guesses, and we want to make them small. So we want to make a MATLAB thing do, and so this MATLAB routine we could also we could make it a function, or we could make it a while loop. So here I've taken this from a gentleman who wrote a paper, and I thought this was a good just a baseline here. And I use it solving Norton's example 4.1. And I should do that actually with my with the Excel one too. I should plug that in and solve that one too. So I'll try. I think I'll do that during class live. Okay. So here's what each of these things does. We clear the memory. We enter in. Here's just declaring all the lengths that we have in example 4.1. And maybe I need to come back to example 4.1 here. I'll mark that up. And take a look at that in class. I'm looking at my clock and seeing that I'm running out of time. But we'll do it. Okay, we'll be able to handle it right here. Great. But anyway, I established all of that, and you can see that my initial estimate is going to be theta 4 estimate and 45 here. So, theta, okay, so this is my input, this theta. So we have 40-degree angle input. My theta 3 estimate is 20 degrees. My theta 4 estimate is 45 degrees. Okay, so I think I'm just creating a 1-by-1 matrix right here. So I'm setting F. I'm trying to remember what I used F for, but we'll see in here. Okay, so this is going to be the thing. This is my where I'm going to set the tolerance right there. So I say while the norm of this thing is this tolerance right here. So I say, well, here it is a function, but can also be a while loop. So I'm actually using a while loop. So I write out my first function. This is function 1, and this is function 2. Right? You recognize these as being for a 4-bar mechanism, right? These are the two vector loop equations in the x and the y. Then I create a matrix A right there. It's a 2-by-2 matrix, and here in the so here's the derivative. I found the derivatives of those functions up there, and so just as we saw them in the previous page, where we had the sine and the sine and then the cosine and the cosine and the positive. You see where they are. Hopefully I can't go back and show them. Can I go back and show them? I don't know if it'll let me go backwards this way right here, will it? Okay, so you see it down here at the bottom right there. That's going to be our A right in there, right? So now we've right. So there, right there is A. B is just going to be these values F, what we get when we put in boom, 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 boom. Yes, okay. So here are here's the answers that we're going to get with this original estimate right in there, and here's what we get over here in the slopes, and here's just B right there. And all we do is find x, where x we're defining as going to be the differences, right? Or x is yeah, it's the difference between these two. We're really what we've just done is we've they used to do inverting a matrix, but you could see that what we've done is trying to go back. It won't let me go back. There you go. Yeah. So what we've done is we've solved for x right there. We've solved this equation right here for x. I think we might have, did we make him negative? Let's see if we make him negative right here. But we solve for x. Right, so we're in this while loop, and we solve for x by dividing a by b, but we're using this little symbol right here that helps us do the inverse matrix right there. This is like a shortcut for the inverse of the matrix. And now we're going to have a new estimate right here. So we had this original estimate that was up here that we fed into the thing, but now what we're going to do is we're going to add in the estimate of this guy right here, because of this. This right here is going to be a column matrix, so we're just going to add in the top, and then we add in the bottom to the 401. And then we try it again right here. So I rewrite this thing out. I think there's like a more abbreviated way I could write this thing out here. And then I set, I fill in this F right here with what we had, right? And then we end. And so this thing is going to keep trying out this until it makes the norm of this guy beyond this threshold. And then when I'm done with it, after it's got beyond that threshold, I am going to go ahead and give an output here that says what these angles. I'm going to turn them back into angles. So let's take a look at the thing that we had set up before. And this is the one that we had. Okay, so now all of a sudden these are going to be in millimeters. So I'll just delete what they are. And for our initial guess, let's see, or for our initial thing, we have that it's going to be L1 is 100. L2 is 40. These are all millimeters. L3 is 120, and this is 80. Okay. And in terms of our input angle, I should say that we have an input angle of 40. So I'm going to say that it's going to be radians of 40 degrees right there. Boom. So there's our input angle right here. And so we're going to take an initial guess right here. I'm just going to say 1 and 2. I mean, I don't know what these things are, what it's going to turn out to be. So I'm going to hit my solver over here again. And let's see, let's try the thing out. Okay, so the answer to this came out to be 20.3 and 60.9, no, that was the other one. It didn't actually, they actually didn't solve this one. That's kind of funny. In the in the example problem, it was kind of an odd thing right here. Why didn't they show me? Maybe I'm overlooking it in the book here. Right here. So here's our 20.3, and here's the crossed version of the thing. And they say the solution is shown in this figure up above right here. But okay, so you see 57.33. So they plug that guy back in. So you can see that we have our 57.33. So we got that right there. So this is what that example is telling us to do. But now let's implement it in MATLAB. So I'm going to go ahead and just grab all of this and paste it into MATLAB, which I don't have on my computer. So I have a blank M file that I've placed in here, and I've hit pasted this into place, and I can save it as something. So where we go, save as. Where the hell save as? I don't even know. Here, I got save. It doesn't matter because it's going to delete it anyway. So I'm just going to, and then I can hit run, which I don't even see anymore. Man, I don't know how to use this. There you go. I'll hit run, and boom, there you go. And here are the angles, and they're 20 and 57.3. And so that's pretty much, it's a useful thing to know how to do, but it's, I mean, in MATLAB, it's pretty, it's pretty confusing to try to figure out like what it's actually doing until you see some description and the accompanying thing. So I'm going to do another example with a more complicated example. But here is a core code, and I want you, when you're trying to create a MATLAB code to be able to figure out the position analysis of the thing, you could run this multiple times for different positions so you could get a full rotation of the thing. So that's something that we want to be able to do, to be able to create, like, say, a coupler curve out of this thing. Because once we have this position, once we have those theta 3s, now we can just extend a vector off of the end of the thing and come up with the coordinates that are associated with those angles. So I think we're done in this part right here. It says 15 minutes.